Have you ever really thought about how we get clean, carbon-free energy from, well, a rock that's pulled from deep within the Earth? Today, we're going to pull back the curtain on the incredibly complex, often dangerous, and totally fascinating process behind nuclear fuel. It's a journey that takes raw stone and turns it into one of the most powerful substances on the entire planet. So let's just start with this mind-blowing fact. This tiny little pellet, about the size of a peanut, holds enough raw power to supply thousands of homes with electricity for a whole year. I mean, how is that even possible? Well, that's exactly the question we're going to answer. So here's our roadmap. First, we'll dive into the incredible energy packed into just one of those pellets. Then, we'll look at the science that unlocked it all. We'll take a trip to a super high-tech mine, see how the atoms themselves get separated, and finally, watch as the fuel is forged to, well, power our world. Okay, first things first, let's really try to wrap our heads around the amount of energy we're talking about here. It's one thing to hear a number like 1 million kilowatt hours, but it's something else entirely to see what that actually replaces. To get that same amount of energy, you'd need almost a ton of coal, or a huge barrel filled with 150 gallons of oil. This incredible energy density is what makes nuclear power so potent. But to really understand the why behind it, we need to take a step back and look at the science. You see, the story of enriched uranium isn't just some industrial process. It's actually woven into the very fabric of modern science. And it all started long before anyone even dreamed of the power that was locked deep inside the atom. It took almost 150 years of scientific breakthroughs. From just identifying uranium as an element, to discovering radioactivity, to finding the neutron, which is really the key to the whole thing. And then finally, in 1938, scientists proved that a specific type of uranium could actually be split, releasing a massive amount of energy. And this right here, this is the central challenge. The uranium you find in nature is made up of different versions, or isotopes. Almost all of it, 99.3%, is stable uranium-238. The special reactive isotope that can actually sustain a chain reaction, uranium-235, makes up less than 1%. It's incredibly rare. So here's the bottom line. To make nuclear fuel, you have to bump up that tiny concentration of U-235. And that whole process? That's what we call enrichment. It is the absolute heart of turning natural uranium into a fuel source we can actually use. And the level of enrichment, well, it means everything. For generating electricity, uranium only needs to be enriched to about 3 to 5% U-235. But for nuclear weapons, you have to enrich it to over 90%. That massive difference is the very fine line between clean energy and devastating power, which is exactly why controlling this technology is such a huge global concern. Okay, now that we've got the science down, let's see how this all works in the real world. How do we even get this rare element out of the ground? Well, the journey begins deep underground, often in some of the most remote places on Earth. So we're heading to a mine up in Canada, where the ore is unbelievably rich. We're talking up to 100 times the global average. But there's a big problem. The ore is buried under this thick layer of water-soaked sandstone, which makes traditional mining pretty much impossible. The solution is just an incredible feat of engineering. What they do is drill hundreds of holes and circulate this super chilled brine through them, freezing all the groundwater solid. This creates a massive, completely impermeable wall of ice, which lets them safely get to the ore without the whole mine flooding. It's pretty amazing. And because this ore is highly radioactive, nobody actually goes down there. The entire mining operation, from the drilling to the extraction, is all done by remote control. The workers are yards away, safe in a control room, protected from both the radiation and the physical dangers of mining. So, we've got the raw ore. Now comes the most complicated part of this entire journey: separating those two nearly identical uranium isotopes. This is where brute force geology smashes right into high-tech physics. First, the ore is crushed up and dissolved in acid. Then, after it's purified and heated, it gets converted into a special gas called uranium hexafluoride. Now, why a gas? Well, because that's the only state of matter where you can actually separate the isotopes effectively. This gas is then fed into thousands of centrifuges, all spinning at unbelievable speeds. And because U-235 atoms are just a tiny fraction lighter than U-238 atoms, they get pushed toward the center. This lets them siphon off that rare U-235, slowly but surely increasing its concentration. What you're left with is this dense, dark powder. So, we've done the hardest part. We've mined the ore, and we've enriched the uranium. Now it's finally time to forge this powerful powder into the final product that will actually go inside a nuclear reactor. And just to give you some global context here, this entire industry really relies on just a handful of key players. Over 60% of the world's raw uranium comes from only 3 countries: Australia, Kazakhstan, and Canada. At a manufacturing plant, that enriched powder is pressed into those tiny pellets we saw at the very beginning. They're then baked for 24 hours until they're incredibly dense, and then they're stacked into zirconium tubes to create fuel rods. Finally, those rods are bundled together into a precise fuel assembly, all ready to go into the reactor. Once it's inside the reactor core, neutrons start splitting the U-235 atoms. This kicks off a self-sustaining chain reaction that releases an absolutely immense amount of heat. And that heat, it's used to boil water, which creates high-pressure steam that spins massive turbines to generate our electricity. But after about a year or so, the fuel is spent. And this brings us to the other side of the nuclear power story. After producing all that clean energy, we're left with highly radioactive waste. Right now, there are over 700,000 spent fuel rods just sitting in cooling pools around the world, waiting for a permanent solution. And that leaves us with one final and really crucial question. The journey from the mine to the reactor gives us incredible power, but it also creates a challenge that's going to last for thousands of years. So as we look to the future of energy, we have to ask, what do we do with what we leave behind?